Hello. Today I would like to talk to you about the Koch snowflake. And so with this, we start out with the seed, which is an equilateral triangle. And then onto the seed, what we do is we have the first iteration is we're going to take, and for each flat surface we're going to add an equilateral triangle. So we see that after we do this, that'll be our first iteration. Our second iteration will add to each flat surface another triangle, equilateral triangle. Each time we add an equilateral triangle, what we have is we have a triangle that's the side length is 1/3 the length of the previous side. So there's something called the replacement rule. Okay, so basically the replacement rule just says that you start with a shaded equilateral triangle. You start with the shaded one, and then the replacement rule is you replace each boundary, which is a straight edge, you replace each boundary with a crinkled version. In other words, you put in the triangle to that boundary. So that's the replacement rule. As the iterations go on and on, the figure itself gets fairly complex. So so what happens with the length of the sides? You start with the seed, and then the length of each side of the first iteration is 1/3 the length of the seed, and then the length of the next side is 1/3 square, or 1/9. The length of the next iteration, so this is the first iteration here, this is the second. Now when you get to the third iteration, the length of the side is 1/3 to the third, or 1/27th, and so on the third iteration. So after many iterations, what happens is the snowflake becomes what we call visually stable. Visually stable. So what that means is the naked eye can see no difference after you keep adding smaller and smaller triangles. Your eye cannot see that. Okay. Now, some things about the Koch snowflake that you would like to know probably are that the boundary is an infinitely jagged Koch curve. The Koch curve. So that's the boundary, and it's infinitely jagged. And then also the Koch snowflake has what's called self-similarity. So if we zoom in, if we did many iterations and then we zoomed in really small on one of the tips of the snowflake, we would see the same exact pattern after many magnifications. So it has self-similarity. And the self-similarity in this Koch snowflake is infinite, it's universal, and it's exact. Alright? So, in nature, there is this pattern that we see. Fractal, this is fractal, it's a geometric fractal. And we see this also in nature in, like, a head of cauliflower. We'll see that. So when you take a head of cauliflower and you zoom in on the head of cauliflower, you see the same pattern repeating itself. But this time the self-similarity, it doesn't keep on going infinitely. So what happens with the cauliflower is it's approximate self-similarity. Alright. Some other things of note about the Koch snowflake. It has a relatively small area but infinite perimeter and infinitely long border. So it's a relatively small area but infinite perimeter and border, an infinitely long border. And we're going to take a look at that. Infinitely long boundary, I guess we could call it. Alright. Okay, so we'll take a look at some of those just in a minute.